Oh, class. Okay, so I'm going to talk about something called the double slit experiment. And so I kind of drew it here. We've got a screen with two very narrow slits that light can pass through. Now I should point out this drawing is not exactly to scale. Typically these slits are extremely narrow, and D is a distance between them that's also very small, like millimeter range, where L could be a meter or something. But just for the sake of the drawing, kind of exaggerated some of these distances. Now, this double slit experiment was done by Thomas Young back in the 1800s. And mentioned as previously, Isaac Newton wrote a book called Optics, where he considered light to be a particle. And he actually explained a lot about light, even though his model was not that great. The idea of treating it as a particle. But that caught on, probably because of Newton. And for a while, light was considered a particle. But then Young did this experiment which showed that light has wave-like properties as well. Mainly interference, which we saw in mechanics. We can look at interference of mechanical waves, like waves on a string or something. And this Young showed that the same thing happened with light, which is extremely difficult to explain with the particle theory. So the idea is, let's say we have two competing theories about what light is, particles and waves. So say we have a source of light, and we picture light as particles. So we have a beam of particles. If they hit the wall, they stop. If they go through a slit, they can pass through. So what should we expect from, say, a particle picture? So if light consists of particles, let's look at it from a different perspective, where we look at the intensity of the light at any location on the screen. So you figure like behind the two slits, there's going to be a lot of light because they can, just pass right through and hit. But off to the side or in the middle, not so much. So what you would expect from the particle picture would look like something like this, where we're plotting the intensity of the light as a function of position. So there's a lot of light behind this slit, a lot of light behind this slit, but really nothing anywhere else. So that's a particle picture. Now, what if light consists of a wave? So we have these wave fronts. I'm going to get rid of this D, maybe I'll put it there later. Let's say we have some wave fronts coming towards the slit. And in general, let me do this off to the side. Say we have something like this, and we have a wave front that, hits this opening. What's it going to do? What's a wave front going to look like afterwards? One idea might be that it would look something like this, where, the part that hits the wall is blocked off, but the rest of it passes through. This is not what actually happens, though. When light goes through an opening, it spreads out. That's something called diffraction. And, so the wave fronts would look more like this. They would spread out. And if we have a very narrow slit, we can consider this a source of spherical waves. And so we have these two spherical waves that are going to meet on the screen. And remember, when two waves combine, the intensity, or the amplitude of the wave, which is related to the intensity, that amplitude depends on the phase between them. They can interfere constructively or destructively. Okay, now there's a few complications I don't want to get into here, but just like waves, or you look at sound waves. Say you have two speakers producing sound waves, and you want to know what the interference is like. we usually consider waves that are in phase with each other. So say the two speakers are hooked up to the same power supply and they're oscillating in phase with each other. And we want to make sure the same occurs with light. So we're going to say that these waves are in phase. So we have two sources of waves, and they're going to meet on the screen. And we want to look at where we would get constructive interference and where we would get destructive interference. So to start out, let's go get a line right down the middle. Let's call this y equals 0. Now, what would we get at y equals 0? Get rid of this picture. And let's look at the wave picture. We've got our two slits. Here's the screen. And y equals 0. We're just looking at it at a different perspective here. That's right across from the two slits, like right in the middle. Again, we have two sources of light that are traveling the same distance. So if they start out in phase, which again, we have to be careful to set up the experiment in a way that it does that. When they meet up at y equals 0, they're going to travel the same distance, and so they're going to still be in phase when they hit the screen. So that would be constructive interference. Well, we should get that's all we know right now. Is at y equals 0, we should get constructive interference. That'd be high intensity. It'd be bright, right across from the two slits. And look, but if we move away, let's say we look at a point here, and the light from slit 1 has to travel this distance, where from slit 2 it has to travel this extra distance, and that extra distance is going to introduce a phase difference between them. And so we want to look at it like, what kind of interference, where are we going to get, say, let's start with destructive interference. What are the conditions for destructive interference? And if you have two sources that start out in phase, they have to be off by half of a wavelength. So if we picture a sine wave or something starting, we'll just start it here for convenience. You know, if the other one is off by half a wavelength, you know, this one starts at 0 amplitude going up, half a wavelength, it'd be 0 amplitude going down. Well, no, they start out in phase, I'm sorry, but they would have to travel this extra distance of half a wavelength. So let's say that this extra distance that it has to travel, the path, we'll call it the path length difference. So delta is, say, d2 minus d1, where this is d1 and this is d2. These are the paths that the light has to take to reach this point on the screen. And if delta is half a wavelength, if the path length difference is half a wavelength, these two start out in phase, and after this one travels that extra half a wavelength, so from this point to here, this is equal to d1, we'll say. Like from here to here is d1, then they're exactly out of phase at this point, and they travel the same distance, and so they'll be out of phase at that point as well. And that is destructive interference. So if delta is half a wavelength, we get destructive interference. Now, if delta is equal to 0, we already considered that, we get constructive interference. Delta equals 0 at y equals 0. You know, d1 equals d2, the difference is 0, and so that's constructive interference. So these are the basic conditions for constructive and destructive interference, and it depends on this path length difference. Okay, now how do we relate that? We have a geometry problem now, how to relate what type of interference, like at any point on the screen, what type of interference are we going to get? So I'm going to erase this a little bit and redraw just the rays without the waves associated with them. Okay, so here's, let's say we want to, or let's just look at some point on the screen. And we mark off a distance here so that these two are the same distance, and that would make this equal to delta. And so basically we have a triangle here, and remember this side was D. D is the separation between the slits. You can get rid of these wave fronts just to have some room to work with. Okay, now remember I mentioned I exaggerated the geometry here. Let's say that this is our barrier and this is our screen, and the two slits are very close together. And so let's say this is our point P, which is here. There's an angle, from this horizontal line, this perpendicular line, to the point P, which is theta. And basically that would be this angle here. Now we're making a little bit of an approximation because theta would be from the center to point P, but the screen is so far away that basically these two lines are virtually parallel to each other. And as far as, so this angle is essentially theta. Even though it's a tiny bit off, not enough for us to worry about. Okay, and that would make this angle theta as well. So this picture is getting a little cluttered, but basically we have this triangle here where this is a right angle. So that's a right angle. So if this angle is theta, that would make this one 90 minus theta. That one is theta. And we can see from this picture, sine of theta equals delta over d. Okay. Now let's look at this picture. We can say tangent of theta is y over L. So like y is the distance from y equals 0 to our point P. We can relate these soon. But basically the conditions for constructive or destructive interference are right here. These are the basic conditions. However, they're not the only conditions, because you can add an entire wavelength. Like if we have a wave, if you pick any point on the wave, it has a certain phase. If you add a full wavelength, it's a completely periodic function, and so you don't change anything by adding a full wavelength. So overall, the conditions for constructive and destructive interference, something's got to give here. Let's see if I can just cram it in here. So this would be for destructive, and this is for constructive. Where m is any natural number, 0, 1, 2, 3, so on. I think 0 is a natural number. It depends on who you ask, though. Seen different books define it differently, but, whatever. So, m equals 0 gives us those basic conditions. Delta equals 0 for constructive, 1/2 lambda for destructive. And again, if m equals 1, delta is lambda. We've just added one full wave. Or for destructive interference, we have 3/2 lambda. So again, we just added a full wavelength. And so that does not affect the phase. So the type of interference we get depends entirely on the phase. So, adding a full wave does nothing. So we can kind of put this together for... Yeah, I don't want to combine these. I mean, we could, just in the interest of preserving room. Yeah, we've got our condition now for any given angle from our double slit to the screen. We can see the conditions for constructive or destructive interference. And so as theta increases, eventually delta is, eventually we'll get delta to be half a wavelength, and then it'll be destructive interference. And then as we increase the angle, we'll get to constructive interference, and then destructive and constructive. So as we increase this angle, we'll get a sequence of bright and dark bands. So what we should expect from the wave picture of light is something like this. So here, right at the middle, we get this constructive interference, and then as we move away from the center, eventually, delta keeps increasing as we move away. So as we move away, eventually it'll be half a wavelength. That'll be destructive. And then it'll be a full wavelength, which is constructive, and then half a wavelength, which is destructive. So we get the intensity going up and down. And so we have two different pictures of light, and they give very different experimental results. And Young did his experiment, and we got that picture. And so that was very strong evidence that light behaves as a wave. And for some reason, it never really caught on too much. It wasn't seen as definitive. The debate continued. Even though it's really hard to explain this experimental result with particles. But yeah, the debate continued until Maxwell came along. Now, what I'm about to talk about has nothing to do with the material we're covering in the class. I just want to briefly mention a little bit more about the double slit experiment. I'm not going to talk about much because I actually added a link to a lecture by Richard Feynman, which, watch that instead of me talking about it. But this was a really interesting experiment. I mean, Thomas Young did this in the 1800s, but they did more experiments in the 20th century. And the results are really difficult to wrap your mind around, like what's actually happening here. Because you can do these experiments with light or with electrons. Because remember I mentioned electrons can behave like waves as well. And you can get the same type of interference pattern using electrons. And so the idea is, let's say you fire an electron at this double screen, or say you have a beam of electrons, and they produce a pattern like this. So they're clearly showing interference. Now, that's easy to explain because you figure, there's electrons going through, and they're waves, and they produce this interference pattern. Makes perfect sense. But there's ways of trying to capture what it's doing. Like, say we lower the intensity. So say we send one electron through at a time. You might think that it might start behaving like a particle, but even sending one electron through at a time, it actually still behaves like this. Now, when the electron hits a screen, it's just gonna, it's not gonna leave much of a signal. But if you accumulate these electrons, you can see they will form this pattern. And so they figure, electron's basically a particle, but it does have some wave-like properties. So if you picture an electron as a particle, it's going to hit the screen at one point. But, what happens when it gets... They kind of thought maybe it would switch back to this particle picture, but it didn't. So even at very low intensities, if you're sending one electron at a time, you will still get this pattern if you wait long enough. So I figured what's happening is the electron maybe goes through both slits, and then it interferes with itself. And this is an interference pattern. That's the only reason this pattern exists is because these waves coming from these two slits are interfering with themselves. So if the electron splits up, or photon splits up and then interferes with itself, then it should be passing through both slits. So then they did a variation of the experiment where you try to determine which slit the electron is passing through. And it should go through both of them. That's the idea. If it just went through one, what's it going to interfere with? So they expected both of these slits to show electrons passing through, even if you send them one at a time. But they found that if you set it up so you can determine which of these two slits the electron is going to go through, it's only going to go through one slit at a time, but then the pattern it creates is going to look like this. And that's a very baffling result. It's like if you're not paying attention to it, it's going to produce a pattern like this. But if you watch what it's doing and try to figure out which one it's going through, it's only going to go through one, and it's going to produce a pattern like this. So it's like if you're not watching it, it acts like a wave. If you are watching it, it acts like a particle. Very strange behavior, this wave-particle duality. Now, it's very strange in a sense. In a mathematical sense, it's not. Experiments like this can be fully explained mathematically. We have a theory. It's all explained by quantum mechanics. But just trying to picture what's actually happening, that's where things get very difficult. Things like this. It's this wave-particle duality, where it always seems to know if you're watching it. And I'm not going to talk any more about this because why listen to me if you can listen to Richard Feynman? So I put a link to his video on this topic. It's very worth watching, but it's optional because we're not going to talk about the wave particle nature. So just if you're interested in that kind of thing, definitely worth watching. But we'll do a few problems during the review, but this is the basic idea. Just like determining where on the screen we're going to get whatever type of interference. Actually, let me show you a picture. So this is kind of what it would look like if you were actually shining light on a screen. You get constructive interference here and destructive in between. And so I don't know if you can see it, but right in the middle, that's the m equals 0 constructive interference. And then the next bright band is m equals 1 constructive. And that's m equals 2 constructive. And right in the middle, this is the m equals 0 destructive, m equals 1 destructive, m equals 2 destructive. So these are the m values we're talking about. So right in the middle, that's the m equals 0 constructive. It look like we have m equals 0 constructive, m equals 0 destructive. So here, constructive, delta equals 0 at this point. This is the m equals 0 destructive, so delta would be half a wavelength. And then the next place we get the special type of interference would be m equals 1 constructive, and then m equals 1 destructive. And, they just keep going. So, but they lose intensity, so, you're only going to have a small number. We usually don't go too high in terms of these m values. But this is a type of interference pattern that we can see with light. Now we'll go over some problems in class, but I think I'll stop this one we cover the basics, and then we'll just do problems in class. So that'll be it for this one.